Okay, let's move to the next problem. A diode in reverse bias has been connected to an inductor of 50 nanohenry. For a reverse bias of 5 volts, calculate the resonant frequency of the circuit. The diode is a PN junction or a P plus N junction with area given to be 10 power 4 per micron squared. Let's move to the next problem. A diode in reverse bias has been connected to an inductor of 50 nanohenry as below. For a reverse bias of 5 volts, calculate the resonant frequency of the circuit. Diode is a P plus N junction with area of 10 power 4 per micron squared, Nd equal to 10 power 16 per centimeter cube, Na equal to 10 power 18. Sketch the quasi-Fermi levels of the electrons and holes in the junction in reverse bias. So the circuit essentially consists of an inductor connected with the diode in reverse bias, right? So this offers a capacitance, this offers an inductance. Therefore, the resonant frequency of the circuit, omega, is going to be given by 1 by square root of LC. So in other words, you're asked to find what the effective capacitance the reverse bias diode is going to contribute to the circuit. So what are we given about the diode? We're given that the reverse bias voltage is 5 volts. It has an Na of 10 power 18 per centimeter cube, an Nd of 10 power 16 per centimeter cube, and an area of 10 power 4 micron squared, or in other words, 10 power 4 into 10 power minus 8 or 10 power minus 4 centimeter squared. Right? So you're asked to find the capacitance, or rather we need to find the capacitance. So we can begin with finding the depletion width in the diode and then the capacitance from there. So let's first find the built-in voltage. At room temperature is kT by Q ln Na and d by Ni squared. And that's going to be 0.0259 ln of 10 power 18 into 10 power 16 by 1.5 into 10 power 10 the whole squared, and this works out to 0.814 volts. So that's your built-in voltage. And so if I now want to find the depletion width in the diode, the depletion width in the diode at reverse bias is going to be given by square root of 2 epsilon s by q into 1 by nd. Now here I'm assuming it's a P plus N diode, so all of the depletion width is going to fall on the N side into VBI plus VR, where VR is the applied reverse bias. So again, this would be 2 times 11.8 into 8.85, 10 power minus 14 into 5 plus 0.814 divided by 1.6 10 power minus 19 into 1 into 10 power 16. Right? And this works out to 0.871 micron. So this is the depletion width of the diode at a 5 volt reverse bias. And so now the capacitance of this reverse bias diode is hence A times epsilon by W. So 10 power minus 4 into 11.8 into 8.85, 10 power minus 14 divided by 0.871 into 10 power minus 4, and this is going to work out to 1.199 picofarad. Right? So now we have a circuit where there is a capacitance of around 1.2 picofarad connected in series with the inductor of 50 nanohenry, and therefore my resonant frequency, as we discussed, omega, is going to be 1 by square root of LC, which is 1 by square root of 50 nanohenry, so 50 into 10 power minus 9 into 1.199 into 10 power minus 12, and that works out to 4.084 into 10 power 9 radians per second. And so if I were to convert this to a frequency, that frequency is going to be omega by 2 pi, which is 650 megahertz. So that is the resonant frequency of the circuit. So what you see here, we see here that as you increase the reverse bias, right, As you increase the reverse bias, what's going to happen to the circuit? So as your VR increases, your W increases, therefore your capacitance decreases and your resonant frequency increases. So now here you have a diode which is functioning as a capacitor whose capacitance changes as a function of voltage. So this circuit is essentially, the resonant frequency can be tuned depending on what the applied voltage is to the capacitor. So it is a voltage controlled tuner, if you will, and it has various applications. Now let's look at the next problem. Here we are now going to look at recombination generation in a PN junction diode. A P plus N silicon junction is formed in an N-type substrate with Nd equal to 10 power 15 per centimeter cube. Assume that generation recombination centers located at the intrinsic Fermi level with the capture cross sections to be sigma n equal to sigma p equal to 10 power minus 15 per centimeter squared. The thermal velocity of the carriers, you can assume it to be 10 power 7 centimeters per second, and the trap density has an average density of 10 power 12 per centimeter cube. You're asked to calculate 1. The generation current density at a reverse bias of 10 volts. How does this current density change as the reverse bias increases? And qualitatively plot the IV characteristic of the diode. So let's first think about the problem. You have a P plus N diode, which means that all of the depletion region is sitting in the N side of the diode. Nd is given to be 10 power 15 per centimeter cube, and you're given, so what's happening here? So when you apply reverse bias, right, you're opening up a depletion region. Now in normal cases, the current that is going to flow in reverse bias in depletion is just going to be the reverse saturation current. But what's happening here is in this depletion region, you're going to have RG centers. Now these may be defects, these may be intentional dopant atoms, what you have, right? And these RG centers basically are going to create a space for electron hole pairs to be generated, so they reduce the lifetime. In other words, in the depletion region, they're going to cause a generation current. And so what you're asked to find is, you're asked to find the generation current density at 10 volts. So the first thing, let's start working. So to calculate the generation density, I need to know the time constant, right, of the carriers in the generation time constant. So you're given Nd, you're given sigma n is equal to sigma p is 10 power minus 15 per centimeter squared. Remember, this is the capture cross section, so it is a measure of the probability that this works as a electron hole pair site, right, the trap. The number of traps you're given to be 10 power 12 per centimeter cube, and the thermal velocity is 10 power 7 centimeter per second, right? And so the time constant in such a system, we know that the time constant for generation is going to be given by tau, which is 1 by sigma nt into Vt. Right? Now here we are talking about the depletion region which is happening in the N region, right? And so you're talking about generation recombination happening in the depletion region inside the N region. And so my tau can be written as, put in the numbers, it's 1e minus 15 into 10 power 12 into 10 power 7, and that works out to 10 power minus 4 seconds or 0.1 millisecond, right? So this is the generation lifetime for this particular diode, right? Now what's going to happen? So at reverse bias, so when you apply a reverse bias, you're going to create a certain depletion width, and as your reverse bias increases, the depletion width increases, leading to a larger area where there's a probability of generation current being generated. So now that you're given the VR, which is 10 volts, this is silicon. So what I'm going to do now is, I know my W, it's again a single-sided junction, so I can write this as 2 epsilon by Q into 1 by Nd into Vbi plus VR. What I'm going to assume in this case, I'm going to assume that BBI is much smaller than VR. Again, this is silicon diode. Your VR is 10 volts, so I can make that approximation. So hence my W at 10 volts, I can calculate it to be 2 into 11.8, just like how we did in the previous problem, into 10 divided by 1.6 into 10 power minus 19 into 10 power 15, right? And this works out to 3.61 into 10 power minus 4 centimeters or 3.61 micron. So this is the net generation, or this is the net depletion width, right, at 10 volts. And once you know the depletion width, the generation current now, and based on Shockley-Hall derivation, the generation current can be written as Igen is Q A N I W by 2 tau n, right? So what you see here is this generation current is dependent on Ni and temperature. So higher the Ni or higher the temperature, you're going to see more generation current because the probability of generation increases. As you increase the depletion width, you have more traps available, so the generation current is going to go up. And it depends on the generation time constant, right? And so you know these terms, so I can calculate the generation current to be 1.6 into 10 power minus 19 into 1.5 into 10 power 10 into 3.61 into 10 power minus 4 by 2 into 0.1 into 10 power minus 3, right? This is going to be expressed in per centimeter squared, right? Because this is, I'm assuming, unit area, and so this works out to 4.32 nanoamps per centimeter squared. So this can be Jgen, right? That is the current density due to generation current is 4.32 nanoamp per centimeter squared, right? And so what's going to happen as your depletion width increases, as your reverse bias increases? So as your reverse bias increases, right, my W increases or my Jgen increases, right? And how does it go? Remember that W increases roughly proportional to square root of the applied voltage. So it's not a very sharp increase, but there is a substantial growth. So therefore I'm going to plot how the reverse bias characteristics of this diode are going to look like. Suppose this is J versus V. So in reverse bias, in the normal diode, a normal diode would have looked something like this, right? A flat current which does not change as a function of applied voltage. However, what you see here is going to have something like this, where you'll see that this current increases as a function of the applied voltage, roughly proportional to the square root of VR. And this thing is going to continue till eventually one of the breakdown mechanisms, be it avalanche or Zener, occurs. In this case, given it's a P plus N junction, it most likely might be avalanche. So till avalanche occurs, you'll see that the reverse bias current will keep increasing. So moving to the next question. Design a varactor, that is a device with voltage dependent capacitance used as a tuning element in microwave circuits using a uniformly doped P plus N junction diode. Assume that the maximum electric field in the junction should be less than or equal to 300 kilovolts per centimeter. The required capacitance variation is from 1 to 2.5 picofarads. The reverse bias voltage applied to the diode should be less than or equal to 5 volts. The built-in voltage is 0.8 volts. Your design should specify the doping level in the N region and the device area. So let's first write down what all it needs to have. So the maximum electric field, right, should be 300 kilovolt per centimeter, right, or 3 into 10 power 5 volt per centimeter. C should vary from 1 to 2.5 picofarads for a reverse bias varying from 0 to 5 volts, right? So remember, as you increase the reverse bias, your capacitance is going to drop down, right? So what you want to see is that the the bare design that will work is when at 5 volts you have a 1 puff capacitance that is provided, right? So let's first begin with the maximum electric field. So the maximum reverse bias I can apply is 5 volts. And I want to ensure that at this point my field should be less than the maximum electric field, right? So my field, my Emax should be less than or equal to 300 kilovolt per centimeter. So if I assume that I'm barely hitting that, then what I have is my maximum electric field in the diode is given by square root of Q times ND times VBI plus VR divided by 2 times epsilon s. I want to find ND, right? In this case, so in this case, I know everything except ND. So therefore, my ND can be given as 2 epsilon s EM squared divided by Q times VBI plus VR, and you plug these numbers in. So it's 2 into 11.8 into 8.85 minus 14 into 3 into 10 power 5 squared divided by 1.6 into 10 power minus 19 into 5 plus 0.8, right? And that works out to 6.9 into 10 power 16 per centimeter cube. So this is the doping density that you need on the N side of the junction, right? So using the maximum electric field and the maximum reverse bias, you are able to get an ND. Now what you know is that it is to give a certain capacitance, and you know that area, by increasing the area, I can increase the capacitance of the structure, right? So what do I need to do? I need to ensure that C min, or the minimum capacitance, is achieved at the maximum reverse bias, which is 5 volts, right? So therefore I need to achieve 1 puff at 5 volts. So therefore, now let's talk about capacitance per unit area. Capacitance per unit area in the diode is given by A epsilon by W, right? Which is A times, if I take epsilon into the expression for W, I'm going to get Q times ND times epsilon S divided by 2 into VBI plus VR, right? So this is this is not capacitance per unit area, this is capacitance. So the capacitance is given by A epsilon by W, right? So from which case, therefore, I can write my A as C min squared into 2 into VBI plus VR divided by Q times ND times epsilon S. And if you work out this is going to work out to 3.16 into 10 power minus 5 centimeter squared, right? So that is the area that will be needed to achieve the given C min, right? So you've now calculated both the doping density and the area of the diode. Let's move to the next question. The current waveform through a P plus N junction is shown below. The effective whole lifetime in the N region is 1 nanosecond. The diode saturation current is 0.1 nanoamp. I1 in the figure is 1 milliamp. I2 is 2 milliamp. The diffusion coefficient of the holes is 12 centimeters squared per second, and the length of the N region is much longer than the hole diffusion length. You're asked to find the voltage across the diode and the change in the minority carriers in the N section long before and long after the transient. Sketch the qualitative time dependence of the voltage across the diode and the minority carrier distributions in the N section versus the distance at time t equal to 0 and at time t equal to infinity, right? So let's look at this problem. So what's happening is, let's first try and understand what's going to happen in this case. So as a function of time, I have a current waveform and I'm switching the current from a certain point to another point, right? So in this case, we're switching from 1 milliamp to 2 milliamp. So we want to know what happens to the voltage across the diode when this happens, right? So what's going to happen when this current flips, right? the diode has a, so think about this, it's a capacitance, right? Diode works like a capacitance. So which means that it cannot quickly move to the higher current. So what's going to happen is the voltage is going to slowly settle and eventually settle to a point such that it supports a 2 milliamp current, right? So let's think about the diode. The diode current very simply is I is Is, Shockley equation, exponent of QVF by KT minus 1, right? And in our case we can approximate this as I as I naught exponent of QVF by KT, because we're talking about large currents and at biases. So when the current is 1 milliamp, what should the voltage across the diode be? The voltage across the diode is going to become KT by Q ln of I1 by I naught, right? Or 0.0259 ln of I1 is 1 milliamp and I naught is zero point 0.1 nanoamp, and so that works out to 0.417 volts. And when current goes up to 2 milliamps, the voltage across the diode has to increase in such a way that the new voltage is V2 is KT by Q ln I2 by I naught, right? And as expected, you don't expect a huge voltage change because the current is exponential to Vf, and so this is 0.435 volts, right? So the voltage across the diode before the transition is 0.14417, after the transition it has to jump up to 0.435. Right? Now what's happening in the diode? Remember, if you think about the diode, when you look at P plus N diode, right? So this is P plus, this is N, this is your depletion region. You have a certain charge density, right? A minority charge density, and this is supporting a 1 milliamp current. Now, when you change the voltage, the current to 2 milliamps, there has to be more charge which should be supported inside. So you're essentially talking about a certain time required for the stored charge in diode to go up from what it was at 1 milliamp to what it was at 2 milliamp, right? And that is what we want to understand. What is that amount of charge that needs to be stored in the diode, right? So if you think about the total charge in the diode is going to be 0 to infinity, because it's a semi-infinite diode, of delta Pn. We know that it falls exponentially in the neutral region of the diode. In other words, it's delta Pn into Lp. And how do I find Lp? I know D, I know tau, so I can find Lp. So I can write my Lp as square root of dp tau p. My dp is 12 into 1 nanosecond, which is my tau p, which gives me 1.095 micron. So that's the diffusion length, right? And so I need to now know the total charge. Now to knowing the total charge, what do I need? I need to first know the doping concentration on the ND side. But I've not been given the doping concentration. Instead, I know what I naught is, right? So now if I think about I naught in our diode, again, we're assuming it's all areas uniform across. So if you think about it, the I naught can be given as Q times dP by Lp into Pn naught, right? This is a P plus N diode. So which means that I don't know the doping concentration. Because I know I naught and because I know it's a P plus N junction, I can calculate my Pn naught to be Lp by dP into I naught by Q, right? And that works out to 1.095 into 10 power minus 4 divided by 12 into I naught, which is 0.1 into 10 power minus 9 divided by Q, which is 1.6 into 10 power minus 19, which works out to 5703.12 per centimeter cube, right? So that is the minority carrier density in the N region at equilibrium, right? So therefore, if I want to find what is the charge when 1 milliamp was flowing, that is going to be Q times delta P N1 times Lp. Now what is this delta P N1? That is going to be Pn naught exponent of Remember, it's forward bias, right? So that extra charge, that is what is important. So therefore I can write this as, and so when I substitute that, I'm going to get 5703.2 exponent of 0.417 divided by 0.0259 into 1.095 into 10 power minus 4, right? Because that's your LP. And that works out to 9.816 into 10 power minus 13 coulombs per centimeter squared. And later, when I go to 2 milliamperes, that Q is going to go up, and that Q is going to go up to a new value. Again, use the same logic, and that works out to 1.967 into 10 power minus 12 coulomb per centimeter squared, right? So your charge to support that 2 milliamp has to rise up. And so what's going to happen? How is your voltage going to rise up? Your voltage is going to not ramp up immediately. Your voltage is going to ramp up from 417 to 0.435 with a time constant of roughly whatever the time constant is, 1 nanosecond, right? So it's going to ramp up slowly, like a 1 minus e power minus t by tau, till it goes to the new voltage, right? And if you look at the exponential charge density, the charge density is essentially going to be exponential. So if this is the end of your depletion region, this is how your charge density is going to look, right? And as your, so this is Q1 say, and as you go, your Q2 is going to be right here, right? And you see that at x is equal to 0, you have that higher increase due to higher injection. At x is equal to infinity, both of them are eventually going to die down to 0. Okay, let's move to the next question. Design an abrupt silicon PN plus junction that has a reverse breakdown voltage of 100 volts and provides a current of 10 milliamps when the voltage across it is zero point 0.6 volts at room temperature. Assume that if n dopant is in centimeter cube, the minority carrier recombination lifetime in seconds is given by tau is equal to 5e minus 7 divided by 1 plus 2 into 10 power minus 17 times n dopant. The breakdown field in silicon is given to be 40 volt per micron. State all your approximations and assumptions. Right, so we're given again the breakdown voltage. So the V breakdown has to be 100 volts, and we need to give a forward current of 10 milliamps when an applied forward voltage of 0.6 volts. Right. And the last thing we're given is that the breakdown field is 40 volts per micron. So what do we need to find? So then we need to find two things. So what are the parameters that we need to find? We need to find one, the doping on the light D side, on the P side, right? Because that's the lightly doped side of the junction, and that's the part of the junction that's going to control the current. And second, we need to find the area of the diode, right? So first thing is, like what we've done in one of the previous problems, we know the breakdown voltage and we know the breakdown field, right? So if you want to design this, we need to ensure that at the breakdown voltage, the field is 40 volt per micron, right? So in reverse bias, that is when breakdown occurs, I know that half Emax, where Emax is the maximum field in the junction, times W, right? This should be equal to the applied voltage, right? That's the area under the curve of the electric field. Or in other words, if I were to think about it in terms of what we know is that when Emax is equal to 40 volt per micron, I should achieve this when Vap is 100 volts, right? So therefore my W at that point, I need to ensure my W is at least 100 into 2 by 40 or 5 micron, right? So I need to choose my doping concentration on the P side in such a way that when I apply 100 volt, reverse bias, the depletion width is 5 micron. And so we know that in reverse bias, the W is given by 2 epsilon s into V applied divided by Q times Na maximum, right? This is W min. So this gives us the maximum P side doping that I can have, right? That is given by Na, which is 2 epsilon s into Vr or V applied divided by Q into W squared, right? So you can work out this. This is going to be 2 into 11.8 into 8.85 into 100 divided by 1.6 into 10 power minus 19 into 5 into 10 power minus 4 the whole squared. And this works out to 5.2215 into 10 power 15 per centimeter cube, right? So this is the doping on the P side of the P plus N junction. So if you look at the two conditions we needed to meet was using this and the breakdown field, we were able to establish the doping concentration. So now the next thing we need to do is find the area of the diode, right? And how do we do that? From here, we can find out what the current density needs to be, and then using IS and VF and using the Shockley equation, we can find out the current. So first, let's figure out what the saturation current should be. So the saturation current of the diode, IS, it's related because I is equal to IS exponent of QVF by KT. I'll neglect the minus 1, right? So in other words, my IS is going to be I exponent of minus QVF by KT. So at room temperature, that's going to be 10 milliamp into exponent of minus 0.6 by minus 0.0259, and this works out to 8.692 into 10 power minus 13 amperes. So this is the saturation current density or saturation current of the diode if we need to supply 10 milliamp at 0.6 volts. Now what we know is that this saturation current, because this is a PN plus diode, I can write my IS as Q times A times Dn upon Ln into Np naught, right? And Ln is square root of Dn tau n. Right? Now Np naught is nothing but Ni squared by Na. Now we calculated Na previously, so Np naught, I can do this. Now I need to find Dn and Ln, right? Now Dn from Einstein's equation is Kt by Q into mu n, right? So I need to find what the mobility is, right? And I also need to know what tau n is, and tau n is given to be a function of the doping concentration, right? So what I need to do is I can find out, so I can write my IS as QA dn by square root of dn tau n into Np naught, or QA square root of dn by tau n into Np naught, right? So now my Np naught in this system is going to be 1.5 into 10 power 10 the whole squared, which is Ni squared, divided by what we calculated, 5.22 into 10 power 15, and this works out to 4.31 into 10 power 4 per centimeter cube. Now tau n we know is dependent on the doping concentration, so it's 5 into 10 power minus 7 divided by 1 into 2 power minus 17 into 5.22 into 10 power 15, and that's 0.45 microsecond. So that's your minority carrier lifetime, right? So you know the minority carrier lifetime, you know the mobility, you know the Np naught, so from which you can calculate your A, and your A works out to be 0.0186 centimeter squared, right? So using the forward bias condition, you can get the saturation current density. Knowing the saturation current density, you can then calculate what the area needs to be because you know the doping concentration in the system.